Thank you, Andreas, and welcome back to the last part at today's Info Day. And in the last part, we show always, a few tips and tricks, and really often or highlight, frequently asked questions about some stuff and so on. And in this case, I will show you, or we talk about timber concrete composite floor slabs and its design. Yeah. Especially when we talk about vibration. So I will not do any ULS design. It's just SLS design, means in this case only vibration design. Okay, so I made a video, but unfortunately it's only in German because of beam elements. But today we talk about surface elements. So we have a laminated timber ceiling. So not a cross-laminated timber, it's only a laminated timber ceiling. But so we have no stiffness in this direction. And on top we have some concrete, and we connect the concrete to the timber somehow. So we get here in this example a spring constant of 1720 meganewton per cubic meter. And yeah, the example comes from this source here on the bottom. It's from Erläuterung zu DIN 1052 or DIN 1052 in German. It is the guideline for the old German timber code. And on page 93, you can follow this example. They did this example by hand calculation with analytical equations, and we compare the results now with the FEA analysis. Okay, so we have a slab 8 meter by 12 meter, and the mass is 595 kilogram per square meters. Okay, so how we do this? So let's go back to RFEM, and let's start with the timber. So I will create a new material. Watch out, it is they have used 10,000 Newton per square millimeters, not 11,000 as C24, but in this case we can simply use a C22, which should have 10,000 Newton per square millimeters. Okay, then I click OK, and we have the height of the timber is 200 millimeter and the concrete is 100 millimeter. So I will enter 200 millimeter, and of course that's still an orthotrophic surface. Otherwise I will get an error message during the analysis. And you see here we have the X direction with a strong M modulus and the weak one in Y direction. In this example we can directly set it to 0 because in the hand calculation from the source, no stiffness was considered from timber. There's a tiny stiffness, but of course not much. All right, so it's an orthotrophic surface with 200 millimeter. Okay, so it has 8 by 12 meters. Let's double check, 12 meters and 8 meters. Okay, then I will copy this surface and I will create a concrete. So the thickness was 20 centimeters and 10 centimeters means we need to lift up this concrete surface by 0.15 centimeters from center to center. Okay, so we need a new material here. Let's check. They have used 30,000 Newton per square millimeters. So we should use a concrete with 30,000 too. It's a C2024. Okay. But it has only 100 millimeter, of course. So we will switch this to 100 millimeter. And afterwards, let's check if everything is correct. We activate the thickness for the surfaces. Okay, and when we zoom in, we see directly, okay, so this is the concrete from here till here, and from here till here, the timber, which looks fine. Okay, So what we need to do now is we need to connect the concrete slab with the timber slab. And what possibilities we have, I will show on two examples. So we have two ways to do this. The first way, I start with a contact solid. So I select these two surfaces and say create solid with contact. Okay, you see directly we get some boundary surfaces. These boundary surfaces have zero stiffness because they get the stiffness from the contact solid. We will define this contact solid. Okay. And we select the contact. So it is the contact surfaces, so surface 1 and surface 2, okay. Perpendicular to the surface, we want to consider full force transmission, and here parallel to the layers, we want to consider this elastic behavior, and the spring was 1720 meganewton per cubic meter, and this value we will enter here. So we are in kilonewton, so I will add 3 zeros. Okay, that's it so far. Let's double check. On top we have this concrete, maybe better to select standard here. And on the bottom side we should have this timber. Okay, good so far? Yeah, okay. We will support the slab. Okay, it's simply supported on this side and on this side. In X direction, I will also consider a tiny spring to keep it stable. Otherwise, there is no support in XY plane, and with the springs, I fix it. I fix this structure, but since we do not use any load in YX plane, we use only load. We'll use only the mass in Z direction, perpendicular to the surfaces. Okay. So this line and this line. Okay, I will add a load case. So load case 1, that should be the mass. The self-weight is already included in this 595 kilogram per square meters. So I define here directly the force of 5.95 kilonewton per square meters. And let's take care of the FE mesh size. So maybe we will switch to 0.2 meters, which should be absolutely fine for this example. All right. That's one option. I will show you the second one. For the second one, I will copy the surface via drag and drop. And in this case, I will use the element surface releases. Okay, I will create a new one, a new surface release. I want to release a new, another surface. So you see here, how does it work? So we have one solid or one surface and another solid or another surface. And in between, there should be this hinge information or this release information. Okay, so here you see we have an advantage because we can control both directions independently. The contact solid, there is only one direction. So X and Y is always the same value. Here we can distinguish, but to compare the results, I will use the same as for the contact solid. Okay, good. And I can release the object here, the same what I did with the line releases, but there is no element until now what I can release, but it doesn't matter. I just click the OK button, and when I click on the surface, you see, there is already a surface. And this surface, I will add it. It's a zero surface, but no big deal. I will switch over to orthorhombic and I will assign this timber surface. I just need to adjust the thickness of the timber by 200 millimeter. Okay. And now I need to set this concrete surface, or I need to create an eccentricity for this concrete surface by minus 150 millimeters. Yeah, and now I have the same model. Oh, not the same, I forgot the supports. So on the left side and also on the right side. Okay, so yeah, let's run the analysis for load case 1. Meanwhile, we check what is the solution from the analytical equation from the example. It is 9.5 millimeters. Okay, let's go back and see the result. Yeah, it's good, but it's still a bit away from the 9.5 millimeters. But you can see it here in the center. Yeah, we have already the 9.5 millimeters, but not here on the outside. Yeah, it comes because of the concrete and the Poisson effect. Of course, in the hand calculation or in the analytical equations, this Poisson effect is not considered, and therefore I will neglect it here too. I set it to 0. Okay, then start again. So we had 9.5 millimeters. We have 9.6 now here, and we have 9.47 on the right side with the surface releases. So it fits perfectly with the result from the analytical equation. So they write here, okay, it's bigger than 6 millimeter, and therefore the eigen frequency of this structure is higher than 7.2 hertz. This was the limit in the old German timber code, and yeah, the new limit in the Eurocode is 8 hertz. But there is always a relation, yeah, between the deformation and the eigen frequency. So I did a small article about this issue. It's explained here. When you go to the knowledge base on our website, you will find this information, and inside there is a PDF file what I have created a few years ago, 2013 already. And here you can see the relation between for a simple one-span beam. The relation is, this equation, maybe this is well known from literature. So for Eurocode 8, for Eurocode 5 and the limit of 8 hertz, we have around 4.9 millimeter. So if the deformation of this one span beam is lower than 4.9 millimeter, the eigen frequency is automatically higher than 8 hertz or 8 hertz exactly. And in case the deformation is bigger than 4.9 millimeter for a one span beam, the eigen frequency is smaller than 8 hertz. That's just a simplified rule. Okay, good. Then let's go further. Yeah, they prove the natural frequency. So in this case, it should be 5.87 hertz. Okay, it's really low, and they write here some additional design requirements are necessary, the same as in the Eurocode 5, but of course Eurocode 5 does not offer or does not provide any information when the frequency is lower than 8 hertz. There are some literature and approaches how to deal with it, for example, from this code or from the source I mentioned, or from other literature. Okay, so let's check the eigen frequency, and we will check it not directly in RFEM, or we cannot check it directly in RFEM. We need an add-on module called RF Dynam Pro. So this Dynam Pro add-on module is based for forced vibrations or for equivalent loads, especially for seismic design and so on. And in our case, I just want to use this first sub module. So there are 4 sub modules inside in this global Dynam Pro module. I use this natural vibration module, and I go here. I will assign my mass. So in this case, I select please use the mass from load case 1. And yeah, in the next step, I can select how much eigenvalues I want to calculate. Of course, I'm mostly interested in the first one. And here I say, please do not accelerate or do not consider the masses in X and Y direction, since I have no support here. I'm only interested in the Z direction. Okay, then let's calculate the frequency. Okay, you see the result here on the bottom side, and accordingly the eigenshape. Of course, for a one-span beam, I do not expect anything else. So we can check the second mode, for example, it's on the right side, and you see here for the first and second mode. So the first mode is on the left side with 4.77 hertz, and on the right side with 5.8 hertz, which is fine, since yeah, the approaches of surface releases and contact solids, it's not exactly the same. So therefore we got different deformations, but yeah, they are close enough. Yeah, and for example, the third mode, that's some torsional mode, but I'm not interested in this mode now. I will check this one here. So eigenshape 5.7, let's say 5.8 hertz. And here in this literature, it's 5.87 hertz. Yeah, which is fine. Then, yeah, we need to check the stiffness under a man load of 1 kilonewton. It's actually the same as in Eurocode 5. We will do this. So I will create a new load case, and I call it unit load. And I will apply this load, yeah, exactly in the middle. And the same here. And I add this 1 kilonewton on this generated node. Yeah. All right. So we run the analysis. And we see, yeah, a deformation of around 0.07 millimeters. Compared to the literature, it's a bit smaller. The reason is because they calculate the stiffness of this wall, yeah, with an effective width. Yeah, they do not consider the whole width 12 meters. The effective width was, I guess, 3.8 meters in this example. So if you would reduce the width of the floor to 3.8 meter and distribute the nodal load to a line load, you will get exactly the 3.8. You will get exactly the 0.083 millimeters. So in this case, this yeah, is a bit too uneconomic, but yeah, it's not far away, so it's okay. Okay, and yeah, the next stuff was the acceleration design. So because our frequency is smaller than 8 hertz, we need to check the acceleration. Empirical investigations in the 80s, yeah, they offered the result that the vibration, yeah, with frequency lower than 8 hertz, yeah, are dependent on the acceleration, and with higher 8 hertz, it's dependent on the velocity. In this case, we are smaller than 8 hertz, so we will check the acceleration. So yeah, there are tests that this velocity check, what is done in the Eurocode, actually is not really design giving anymore, because typical timber floor is, because of acoustic reasons, is already really heavy, and the weight is really high. So therefore, the velocity check mostly is never controlling and not important. But yeah, okay, the acceleration needs to be checked. Let's check how we do it by our hand calculations or by some analytical equations. Maybe you know, yeah, these equations already, or you have seen it in some literature. Yeah, so we have the acceleration A, and we have a mass F. We have a force divided by some mass. Yeah, so this is the force here, and this is the mass, and this 2 times D. D is the damping. This comes from the magnify function. Okay, so before we do this in our Dynam Pro, we need to know what all these factors comes from. So first of all, we have the 700 Newton. This is just, yeah, the weight of the person, which is considered, they consider it with 70 kilogram. 0.1, that's a Fourier coefficient. I have no time to explain it more in detail, but you will find it when you check, yeah, vibration-induced, or you can check this literatures where the topic is about this induced vibrations, and you will find this factor 0.1. And there is another factor 0.4. This is a simplification because you do not move on the same place, so you move around, and therefore this factor 0.4 was introduced. Okay, the mass is nothing special so far, and 2 times d. Yeah, and exactly this I want to consider also, I want to define in our Dynam Pro add-on model. All right, let's go back, or before we go back, maybe we can switch to Dynam Pro. No, we cannot. We need to restart the analysis again because I want to copy already the natural frequency because I need it in the module. In this case, I need the angular frequency omega. So I copy, yeah, the first one. And then let's go to Dynam Pro. So in this case, I need to activate this response spectrum analysis option, or in this case, it's actually a time history analysis with a time diagram. So I can skip the first 2 tabs because they are not important for it. And here I need to define this function, and I copied already this omega, yeah. And this omega I have to enter here. So this is actually, yeah, resonance check. So do not enter the angular frequency of a person, yeah. So when you walk around with you walk with around 2 till 2.45 hertz. So, and 2 times p by the frequency is the angular frequency, but do not use the angular frequency from the person. What you need to do is, that's why it's called resonance check, you need to enter exactly, yeah, the angular frequency from the first eigenshape to get the resonance. Okay, the shift should be 0, and multiplier I write down just a 1 for now, and you see this periodic function, which is fine. Yeah, but we need to consider the force, the correct force. We remember in load case 2, I have defined this unit load of 1 kilonewton. So when we check the force here, which is here on the upper side, so we have 0.1 by 700 multiplied by 0.4 equals a factor of 0.28. Let me double check this on my notes. Yes, it's correct. Okay, so when we multiply this factor by this 1 kilonewton, we get exactly the same force as it's written here. Okay, and that's actually all for this tab. Then we switch over to the dynamic load case. We will do a linear model analysis. And here I can connect this unit load, this 1 kilonewton, with this time diagram. Okay, I can use this factor here too and use a factor of 1 here. That's also possible. But yeah, it's okay now. Okay, very important are the time steps. They should be really, or they should be small enough to cover all important load steps or time steps, and long enough to cover the resonance. So you need to play a bit around with it. Start with 1 value and then see in the results if resonance occurs already or not. Okay. So, and at least we need to define the damping, and it was given by 0.015 5. I guess that's all. Okay, I need the calculate button and let's check what result we get. We get 0.064 meter per square seconds. So 64. Now we get the result from the dynamic load case. And here we get the result from each time step till 10 seconds. But I'm interested in this dynamic envelope, so which considers all of these time steps. Okay, and here I will switch to nodes accelerations. So we know this node is number 17 and this node is number 18. Okay. All right, so in this example, we get 0. So yeah, it's not exactly the same, but yeah, it is okay. We get 0.032 when we compare it with the result from the analytical equation. We get only 50% of it, and exactly 50% of it. When we think about this equation here on the bottom, what they have used in this example, yeah, they think about a 4-sided supported slab. As you see, yeah, they estimate one, only half of them goes into the half of them goes into this supports and into this supports. So what we need is actually, for our example, is actually this one, because we use it as a one-span beam. So they have mixed it in this literature a bit. Yeah, it was a bit confusing first, but I figured this out at the end. And yeah, if you multiply, so if you reduce, so this is 0.5 by b. So if you neglect the 0.5 by multiplying the whole equation with 0.5, you multiply it also this value with 0.5. So you will get exactly the 0.032 meters per square seconds. So yeah, this is the way to check it. And of course, you can add the supports here and here. So support it on 4 sides and run the analysis, copy the angular frequency again, insert it in the time course monitor, and then you will get exactly this 0.065 meters per square seconds. But yeah, this is your homework, and for me, for me that's all from today, and I hope yeah, everything was clear with this approach and with the defining of the contact solids and the surface releases. Yeah, it's a mighty feature. Of course, for this lab, maybe I would not use this Dynam Pro add-on module when there are some easy, simple analytical equation where you are much quicker. But in case of some complicated structure, or please consider you have a downstand beam here, so you have no rigid support, you have a semi-rigid support, and then it's getting really complicated to get these accelerations, or yeah, these accelerations with analytical equations. Yeah, maybe one thing I want to show you is here this time course monitor. I want to check the acceleration in C direction for node number 18, and okay, maybe. Yeah, you see here, maybe the time step was not small enough. Maybe we should add here another 0. I will do this quickly to get a proper result. Yeah, we saw that the function was not really homogeneous. It was really yeah, there were a lot of peaks and so on. I increase the increments here, and then let's check. Of course, the more time steps you use, the longer the analysis takes, but we'll see the result Still loading. Okay, so you see it was the same result. Okay, it does not change, only for the contact solid. Yeah, now we get the same results for both because of smaller time steps. And when we check this time course monitor, hopefully we get a we get a better curve. Yeah, looks good so far. So you see here how this resonance starts, and the peak is here, and the next value is already 0.01. So yeah, it's a minute. So this value here is already smaller, so it will fall down here. So resonance is here at around 9.95 seconds. So I catch it really good with the 10 seconds. Yeah, okay. So you can evaluate all the results from velocity, from acceleration inside here, this time course monitor. Okay, good. So that was it from my side. And yeah, I will give back to Andreas, and thank you very much.